This video is about RISC design philosophy. All information is from ARM System Developers Guide by Sloss, Symes, and Wright. RISC stands for Reduced Instruction Set Computer, and there are four design rules: instructions, pipeline, registers, load and store architecture. We'll cover the first design rule, which is instructions. RISC architecture provides for reduced number of instruction classes, and the classes are for simple operations which can be executed in one cycle. A operation is a combination of multiple instructions. These instructions are synthesized in the compiler or by the programmer, and thus all complexity is at the compiler level. When compared to the RISC architecture, the complexity is at the hardware level and not at the software level, which is at the compiler. Another feature for instructions in RISC is that it is of fixed length, and hence decoding is not needed to fetch future instructions. Being of fixed length, a pipeline can fetch future instructions without waiting for current instructions to be decoded. Thus, when compared to RISC, the advantage is that fixed length instructions over variable size. Hence, decoding an instruction is not needed to load the next instruction, which is a must in RISC. Hence, to execute the same operation, there are multiple cycles needed in RISC, whereas the reduced number of cycles are needed in RISC architecture. The next design rule is for the pipelines. Processor pipelines are execution units, and these execution units execute the instructions which are broken down in smaller units. A unit of an instruction is executed by a pipeline. The pipeline advances one step at a time on each cycle. There are multiple pipelines in a RISC architecture, and these pipelines are can be executed in parallel. Thus, the throughput in a RISC architecture is higher. Instructions are decoded at one pipeline stage, and which is an advantage in RISC, where there is a need of a mini program called microcode to execute an instructions. Pictorially, one can see that in a pipeline, different different states like fetch, decode, and execute can be executed in parallel by multiple pipelines. You can see that in cycle 1, there is one instruction is fetched. In cycle 2, while the instruction is decoded, another instruction is fetched. And in cycle 3, one instruction is executed, another is decoded, and third is fetched. Thus, the higher throughput as compared to the RISC. The third design rule is for registers. Registers are local to a processor, and because they are local, they are faster to access as compared to memory, which is external to the processor. All the data processing operations are performed on the registers, and RISC provides for a larger register set so that the processing can happen locally and in a fast manner. Also, in RISC, a register can contain data or an address. There is no restriction on a register for the data that can be contained in it. And this is an advantage over RISC architecture, where dedicated registers are needed for specific purpose. The fourth design rule is load and store architecture. In a load and store architecture, the data processing operations are separated from the data access. The data is needed to be accessed from memory, loaded in the registers so that the CPU can process the information. A load operation is transfer from memory to register, whereas store is transfer from register to memory. The registers being local to the processor, they are relatively fast, whereas the operations with memory are costly. Data is loaded in registers and processed in RISC architecture. There are no direct operations on the memory. Also, once the data is loaded in the register, it can be processed multiple times. Because there is no need to access memory multiple times or often, the load store architecture provides definite benefits in RISC. The advantage is over RISC, the same is the advantage over RISC because the data processing operations operate on memory directly, and hence the load store architecture in RISC offers better throughput than the RISC.